For the last example, we have a situation where we have water coming in at some point, increasing in height and leaving at a different point. So we have P1 at this point, P2, and there's some kind of height difference between, say, this is Y1, this is Y2. And if we consider the continuity equation, which says that V1 times A1 equals V2 times A2, this is known as the continuity equation, then we can say that the velocity at V2, the higher point, is going to be A1 over A2 times V1. And since these are circular pipes with a diameter, we can say this is pi r1 squared over pi r2 squared times V1, and the pi's will cancel. So we have r1 squared, which is the radius at the lower end. It has a diameter of 2, so it's 1 centimeters quantity squared, over the diameter at the top is 1 centimeter, so that would be a radius of 0.5 centimeters quantity squared, times the velocity of 1.5 meters per second. And this will give us a velocity at the top of 6 meters per second. And now if we use Bernoulli's equation, which says that P1 minus plus 1/2 rho V1 squared plus rho G Y1 has to equal P2 plus 1/2 rho V2 squared plus rho G Y2. We can use this equation to solve for P2 and say that from that Bernoulli equation, P2 would equal P1 minus 1/2 rho. And if I move this term over to the left-hand side, I can factor a rho and a 1/2, and I get V1 squared minus V2 squared. And then if I look at, I'm sorry, this should be a plus here. And then if I get this term over to the left-hand side, I would have a plus rho G Y1 minus Y2. And notice we know what P1 is. We know what rho is for the liquid, which is water. We know the velocities, and we know that the difference in height is given as 5 meters, right? So Y2, since Y2 is higher than Y1, this would be minus 5 when we plug this in. So if we plug in our values, we get a pressure of 4, absolute pressure of 4 atmospheres. So P1 is 4 atmospheres. times 1.01 10 to the 5th Pascal per atmosphere plus 1/2. The density of water is 1,000 kilograms per meters cubed. V1 is 1.5 meters per second. Quantity squared minus 6.0 meters per second. Quantity squared. I'm going to continue on the next line. Plus 1,000 kilograms per meters cubed times 9.8 meters per second squared times a minus 5 meters because y1 is lower than y2. And if we do these calculations, excuse me, we get about 3.3 times 10 to the 5th Pascal. And if we want to change this to atmospheric pressures again, we can say that 1.01 times 10 to the 5th Pascal is 1 atm. So this is approximately 3.3 atm. So depending on which unit we're looking for, we have that. So we found the speed, we found the pressure. We're asked for the volume flow rate for the bathroom, and remember that the volume flow is defined as the change in volume over the change in time, but that is either A1 V1 or A2 V2. So let's take this part and plug it in. This is going to be pi times 0.5 10 to the minus 2 meters, which is the radius squared, times the velocity at that point, or the speed of the water at that point, which is 6 meters per second, and we get a flow rate of 4.7 times 10 to the minus 4 meters cubed.